Hello students, welcome to KlassPM. In today's class we are going to discuss about the types of molecules and their rotations. Based on rotations which occurs in the molecules are classified into 4 categories. Now those 4 categories we will study in today's class. Before going to study about those 4 types of molecules, now let's study about a particular word called moment of inertia. So what is momentum of inertia? We will study first, then it is easy to understand for us what are the types of molecules based on their rotation. So the first topic we are to study about, that is moment of inertia. So if you take the moment, we have 2 types of moments we will study, that is linear momentum and angular momentum. Linear momentum and angular momentum. So linear momentum is mass into linear velocity, and angular momentum is moment of inertia into omega, which is angular velocity. Here m is the mass and v is linear velocity. Here I is, this is the I we want, momentum of inertia, and this omega bar is angular velocity. So what is linear momentum, angular momentum? Let's linear velocity. What is angular velocity? Linear velocity is the, in 1 second, a particular object, how much distance traveled in a straight line, that is linear velocity. In 1 second, a object, how much distance it traveled in a straight line, that is, it's a linear velocity we can define in the simple terms. So what is the angular velocity? In same 1 second time, a particular object, how much angle it covered, how much angle it traveled. So here we are measuring in a straight line the velocity. Here we are measuring in the angle, how much distance it covered in an angle in 1 second time, that is angular velocity. Now what is this moment of inertia? For us the important term is here moment of inertia. What is momentum of inertia? In a simple term I want to tell the momentum of inertia. For example, this is the object I have. Now I want to put this one in the rotational motion. So it has to rotate. It has to rotate. So to make this object to rotate, I should give some torque. Torque in the sense, in physics we will use this word. It is nothing but one kind of force only, which is putting it in the rotational moments. The force required to put an object in the rotational momentum, it's called torque. So simple, you can say the force. So this object is stable now. Now I want to put this object in the rotational moment, like it has to rotate like this. Now for that, how much force I am giving? Okay, the force I am giving. So when I am giving force, what happens? It will resist that force to stay in the stable position, same position. So that is called momentum of inertia. Okay, it is giving some resistance to avoid its rotation. So that inertia, if we overcome that inertia only, it goes under rotation. So 2 ways it can define. So the first definition I can give like this, a quantity. That 2 definitions we can give for the momentum of inertia in the 2 different ways. Let's see the first definition. A quantity expressing tendency of a body to resist angular acceleration. Angular acceleration. This is the way we can define. So it is a quantity which is expressing a body's tendency. This body's tendency to resist angular acceleration. So it is resisting to undergoing angular acceleration. It is not undergoing acceleration unless you give more than its resistance force, which is nothing but moment of inertia. The simple way you can try to understand this definition is, it is, for example, I want to put it in the rotational motion, so I have to give some angular acceleration. So now this body is giving some resistance in the form of moment of inertia, that is not allowing it to going into rotational, that is angular acceleration. So another way also you can define this one. The second type of definition you can give is the amount of torque. Torque, I said, it is a force required to put an object in the rotational moment is called torque. So the amount of torque required to rotate an object or accelerate its motion, also you can say, or accelerate its motion. So 2 ways you can define the momentum of inertia. So first definition you can say that it is a quantity that is expressing the tendency of a body to resist the angular acceleration, and another way you can define the amount of torque required to rotate a body or an object or accelerates its motion. Okay, once again I will put it in simple terms. See here, I want to put it in the rotation. So this particular body gives some resistance force to avoid this rotation. That is called momentum of inertia. Or if I want to put this under rotation, how much force I should give? That is called momentum of inertia. Either way you can define. Now, so what is the formula for this one? I is the momentum of inertia. So we have two different formulas for this. One formula you can give when only one molecule is there, one atom is present, it's momentum of inertia. If diatomic molecule is present, two atoms are present, another way definition, another way formula you can give. Let's see what are those formulas. Okay, this is a formula you can give for the momentum of inertia of a particle. So here m is the mass of that particle and r is the distance between center of gravity and the body. Okay, so what is m? M is the mass of whatever you are considering that is an object, and r is the distance between center of gravity and the object. I hope you know what is the center of gravity. For example, this particular object I have taken, if I hold a particular space only, it can stay like this. If I keep it here, it will bend this side. If I keep it here, it will bend it. If I hold it a particular place, then it stays straight. That particular place, that particular point where both side equal mass is balanced, both side keeps the equal mass of an object, that is what center of gravity. In the simple terms I kept this one definition, center of gravity. So you understand, to understand better momentum of inertia, better you study about the center of gravity which you come across in the physics. So center of gravity, in simple terms you can say that for any object there is a particular point that is exactly for entire mass of that object, that is the center point. Okay, at that point its mass is equally distributed. For example, this marker if I take, what is the center of gravity? In somewhere here it is its center of gravity. At this, if I hold at this point, this side it is having equal mass. So I can hold like this. So that is the center of gravity. If two particles are there, if two particles are rotating, this is one particle, this is another particle. If these two particles are, let's take this particle 1, this is particle 2. These two particles are rotating, then what is the momentum of inertia for these two particles with respect to each other? So the mass of this first particle m1 and the mass of second particle m2. And let's take this point is the center of gravity, and the distance between the center of gravity and the first particle is r1, and the distance between center of gravity and the second particle is r2. Now the momentum of inertia in this case, it will become m1 r1 square plus m2 r2 square. So two way you can give. If only single object, single particle is present, that is simple mr square you can give. If two particles are rotating which are in the bond, so in that case what you can do, distance from the center of gravity to the particle is r1, distance from the center of gravity to the particle is r2, and the mass of two particles is m1 and m2, then the momentum of inertia of this particular molecule will be equal to m1 r1 square plus m2 r2 square. This is the way you can do it. Now I hope you understand the momentum of inertia. What is the momentum of inertia? It is a simple term, you can say it is a torque, that is force which puts an object in the rotation. Okay, the force required to put an object in the rotational motion or its angular acceleration, that is called the momentum of inertia. Single particle like this, for a two particles are rotating. If two particles are rotating, then this is the formula you can use. Now we will see what are the types of molecules we have based on different types of rotations. So based on the type of rotations, we have classified the molecules into 4 different types. They are linear molecule, symmetric top molecule, and spherical tops and asymmetric tops. So first we will go to the linear molecule. What are the linear molecules? So for that there is a 3-dimensional picture, imagination required. Let's imagine this marker is a bond, and imagine that, and this side you have a molecule, that is hydrogen, another side you have a chlorine. That you have to imagine here hydrogen and here chlorine. So when it comes to 3-dimensional way, 3 axis will be required, x, y, z axis required. Let's take my x axis like this, which is going through this way, and my y axis is like this, and my z axis is like this. Three axes are there. Let's see the rotation along the x axis. One, it is going like this. Say x axis is going like this. So, and it is rotating this way. Now both here one molecule, here one molecule, now it is rotating like this. Now imagine it carefully. When it is rotating along the x axis, okay, or a axis, what is observing here? The relative position of atoms is changing, not changing. It is same position. They are at the same position but rotating. In this case, the momentum of inertia will be almost zero. It is negligible momentum of inertia because the relative position of molecules is not changing. See here, when axis which is going through this, through the molecules, here one molecule, here one molecule, both molecules are like this. Now imagine this is hydrogen and chlorine. Now it is rotating like this. So hydrogen is at the same position, chlorine is at the same position, but they are rotating in their respective position. So that in this case the momentum of inertia is almost zero. You can negligible. That's why I written IA which is going through this way. Okay, IA, that is zero. Next, another one, the y axis, you can say that it is passing through like this. Now how it will rotate? This is the way you can rotate. So imagine one line through like this, through the center of gravity, and it is rotating like this. It is rotating this way. Now here what happening? Chlorine, this black color is chlorine, and this end portion is let's take hydrogen. So here the line is there. Now I am rotating like this. So now the position of chlorine and hydrogen is changed. Now changed, now changed, now changed. So here what's happening? When I am rotating along this axis, the relative positions of hydrogen and chlorine is changing. That's why here the momentum of inertia is greater. Now imagine third one. Third one is like this way. Now I am rotating this way through this. See, I am rotating like this. Now it is rotating. So what happening? Here chlorine, here hydrogen. When I rotate at 90 degrees, here chlorine, here hydrogen, chlorine, hydrogen, dipole momentum is changing. And because of that, what's happening? Momentum of inertia will be greater. Now in these three cases, in the first case there is no change in the relative position of atoms, so that momentum of inertia is almost negligible. In the IB and IC case, in the second and third cases, that is IB and IC, in both cases the momentum of inertia will be almost equal. So such molecules where the momentum of inertia through one axis is zero, almost negligible, and other two momentum of inertias are equal, in such molecules are called linear molecule. That, for example, you can see the HCl. Second type, that is symmetric top molecule. Now here you need to imagine one more thing. Let's take your center one molecule. Let's take this is the center. Okay, my fist is the center. Now imagine above at the same position one fluorine is there, and here one molecule hydrogen, here one molecule hydrogen, here one molecule. At 120 degrees angle, three hydrogens are there. At the middle carbon is there, and the top fluorine is there. So I have CFH3 or CH3F. I have a molecule like that. In this case, now imagine what kind of changes occurs. Now here top fluorine, this my fist is carbon, and here three hydrogens, imagine. So what's happening here? My first axis IA is going through like this. Now I am rotating this way. I am rotating this way. Here what's happening? Carbon and the fluorine are in their respective position. Here fluorine and here carbon, both are in the same position. You can see in the picture. Now one axis is going through fluorine and carbon. So you are rotating like this. So what's happening? Fluorine in that position only, in the same position and rotating. Carbon in the same position, it is rotating. But three hydrogens with equal weight, hydrogen masses are same, are rotating. So what you can say that here the momentum, since hydrogen position is changing, but what's happening here? Hydrogen position, their masses are equal masses. Because of that, what happens here? Ij will not be zero, but it is very less. Okay, Ij will not be zero, but it will be less. Now second type of rotation, that is along with this. Now here imagine my fist, above my fist what is there? Here fluorine is there, and the three hydrogens are there. Now the second one, now imagine here carbon and fluorine, the center of gravity Inware between carbon and fluorine. It is not with the carbon, it is not with the fluorine. The center of gravity, because hydrogen mass comparing to carbon and fluorine mass, very less, negligible mass of hydrogen. Now when it comes to center of gravity, that is between where? It is between somewhere carbon and fluorine. Okay, I am not saying that exactly middle of fluorine and carbon, because fluorine mass is different, carbon mass is different. So always this center of gravity shift towards the higher mass. Between carbon and fluorine mass is higher, so that it shift towards the fluorine. It is closer to the fluorine, not closer to the when it comparing to carbon and fluorine, it is closer to the fluorine. Okay, now this is going through the center of gravity. Now this is the way it's growing. Here my fist and fluorine, 3 hydrogens at the down space. In this plane, 3 hydrogens with 120 degrees angle, and here top fluorine. Now this is going through the fluorine. Now it is rotating this way. So what's happening? Carbon position is changing, fluorine position is changing, 3 hydrogen positions are changing. Okay, this way rotation. Imagine this way I'm rotating, this way. So that fluorine position is changing. See, 190 degrees. Fluorine from here it came to here. Carbon from here it came to here. And the hydrogens from these 3 positions it came to 1, 2, 3 positions. So the position of all the atoms in the CH3F all are changing. That's why here the IB will be greater momentum of inertia. Next, IC. See, IC is going through this way. Now first one is this way, second one this way, and the third one is this way. Okay, now my axis is going through the center of gravity, this one. Now this is the way it's going. Here below carbon is there, above fluorine is there, and here below plane 3 hydrogens are there. Now I am rotating like this, so that what happened? 190 degrees if I rotate, fluorine will come here, carbon will be here, and the 3 hydrogens will be like this. If I rotate here, fluorine here, carbon here, and the 3 hydrogens are in this plane. So in IC case also, the position of relative position of all the 4 atoms, all the 5 atoms is changing. That's why IC will be also greater momentum of inertia. And here IB and IC almost equal. And here 2 types of, again in this 2 types we can make. If IB and IC are greater than IA, such type of molecules are called prolate molecules. If IA is greater than IB and IC, such molecules are called oblate molecules. Once again here, try to understand. IJ is going like this. So first imagine here center carbon, above fluorine, in the below plane 3 hydrogens are there. First one is going through the fluorine and carbon. So that what happens? Here fluorine and carbon relative position is not changing, only hydrogen positions are changing. So that what happens? The momentum of inertia will not be 0, but it's not greater, it is very short, less. When it comes to IB and C, in IB and IC kind of rotation, the relative position of all the atoms are changing, so that these 2 are equal and greater in magnitude. And if IB and IC is greater than IA, that is called prolate type of molecule. And if IA is greater than IB and AC, that is called oblate type of molecule. And the third type of are spherical taps. In the spherical top, what happens? Now in the previous example, in the place of fluorine, you imagine hydrogen also. Now all the 4 are hydrogen, CH4. In this case, what happens? Whether you rotate through IA, IB, IC, they will not be equal to 0, but it will not be any momentum of inertia. So in the third case, what's happening? Now imagine fluorine in the place of fluorine. The previous example, in the place of fluorine, now you observe hydrogen. Imagine hydrogen. So at the top hydrogen, below carbon, and the 3 hydrogens are at the plane. Now whether you rotate through IA, IB, IC, what happens? The relative position of all the atoms are changing, but here all of them are same hydrogen, their masses are same. So that IA, IB, IC, all 3 are equal, but they are not equal to 0. That's why such molecules are called microwave inactive, because they exhibit symmetry. They are showing symmetry. That's why these are called microwave inactive, we call it as, because there will not be no change in the direction of the dipole momentum, because all of them are hydrogens only. All of them are hydrogen, and that too they are showing symmetry. So such molecules are called microwave inactive molecules. Example, you can take the CH4. And the last type is asymmetric top. Example, you can take the water molecule and CH3Cl molecule also. Here you can see that Here Ij, Ib, Ic, all three are not equal to each other at all. Okay, Ij, Ib, Ic, all of them are, they are asymmetric. There is no symmetry a little bit also. That's why these are called, they're chemical, they're microwave active only, but Ia, Ib, Ic, all three are not equal. Such molecules are called asymmetric tops. Briefly, we will once again discuss this for linear molecule. What happens here? Ij will be 0, Ib, Ic both are equal. Such molecules are called linear molecule. And the second type, symmetric top molecules. Here, two kind of situation there. Ib and Ic both are equal. These two may be less than Ia or greater than Ia. If it is less than Ia, that is called oblate type of molecule. If it is greater than Ia, that is called prolate type of molecule. Third one is the spherical tops. In the spherical top, they are symmetrical. That's why there is no change in the direction of dipole momentum. Such molecules are called spherical tops, and they are microwave inactive molecules. Next, asymmetric tops, they will show all Ia, Ib, Ic, all three-dimensional rotations are almost not equal. That's why they will exhibit different type of rotation, and they will exhibit different type of momentum of inertia. So this is the way you can categorize types of molecules based on their rotations.